Okay, Chapter 17 is chemical equilibrium. So we're going to talk about what that means, and it has to do with chemical reactions, of course. I have this picture here because this is obviously a picture of a cave. You're probably wondering what in the world does that have to do with anything. But this is actually a equilibrium reaction, meaning there's a forward and reverse reaction that makes these stalactites and stalagmites. It's really an equilibrium reaction between sodium carbonate and sodium bicarbonate. So it's like the reaction occurs and then it goes back. So that's what kind of makes these the stalactites and stalagmites. So that's an equilibrium reaction going on. All right, today we're going to go over what's equilibrium and talk about the basics. We're going to look at an equilibrium constant, which is typically pretty easy to grasp. And then we're going to look at our equilibrium constant and some calculations. And we won't get to these until either Thursday or next week. This one right here is the hardest. This is the disturbing equilibrium. It's a long calculation. Tina was laughing because her daughter, she printed out the handout for that day, and her daughter said, "Why did you leave the whole paper blank?" It's just one question on one page. That's a waste of paper. Well, it's not a waste of paper. You're going to use the whole paper for the calculation. So that one is just, it's not hard. It's just tedious. So, okay. Unfortunately, for chemists, most reactions don't go to completion. So you can sit in there all day and all night, and it's not going to go to 100% completion. Okay, so that means that there's a forward reaction going on and a reverse reaction going on. And this is noted by equilibrium arrows there. Okay, so you may have just seen the one single reaction arrow. Okay, but in reality, most of our reactions, not all of them, are reversible. So they can go in the forward direction, but then these products might want to react together, and then they want to go back this way and form back your reactant. Okay, so a lot of chemistry is spent, and a lot of chemists in the lab spend their time trying to tweak reactions, change conditions, temperature, things like that, trying to shift the reaction as far as possible to products, right, to whatever their desired product is. So if we look at what's going on, so A and B are just generic reactants here. And the lowercase A and B, that's just the mole-to-mole ratio, so whatever that would be here. Okay, this is a product-favored reaction. So if you look here, this red is our reactant. So as the reaction proceeds, we consume some of our reactant, right? The concentration's going down. But it never gets to zero. It never completely consumes the reactants. But as the reactants react together and they're consumed, then we get some products, right? So we end up with more products than we do reactants. Okay, at this point right here, this is the time at which we reach what we call equilibrium. Okay, this means, well, I'm kind of getting ahead of myself, but this means that the forward reaction rate is equal to the reverse reaction rate. Okay, so we'll come back to these in a minute to show that. Okay, so what I just said, equilibrium exists when two opposing reactions occur simultaneously at the same rate. Okay, so your forward and reverse is in the same rate, but here in bold, this is really important. This does not mean you have equal concentrations of reactants and products. All right, look back here. This was a reversible reaction. Okay, at this point, the rate of the forward and the reverse reaction was equal. Okay, but look at our concentrations. Okay, I said earlier the products were favored, right? Okay, so just because it's equilibrium doesn't mean that you have equal concentrations of both. Okay, so here you have higher product concentration. Okay, so how I kind of think of equilibrium is the molecules are still continually reacting. Okay, it's just the fact that the rate is equal. So think about if you had maybe like a bucket, okay, and it has water in it. And you put a hose in one side, Okay, and you drill a hole exactly the same size on the other side of the bucket. Okay, so once you get the water in, it fills up to where the holes are. And imagine that you're putting in as much water as you are losing. Okay, the water's still flowing in and out, just like molecules are still moving. They're just going in and going out at the same rate. Okay, so we still have movement, right? We're still putting water in, we're still forming, we're still putting it out. That's the same idea with equilibrium. Okay, you're still moving. It doesn't mean it hits equilibrium and it stops. Okay, it's still moving, it's still going. It's just everything, your concentrations are going to stay constant at that point. Okay, so you're putting water in that situation and you're putting it out at the same rate. Okay, so if you look at this chart here, we have time and the concentrations. Here's the time at which we hit equilibrium, which means the forward and the reverse rate are equal. Okay, the forward reaction and the reverse. Okay, does everybody see what I'm talking about when I say a reverse reaction? Okay, it means so in the forward directions, what we've seen, reactants collide, they break new bonds, form new bonds, and form products, right? Reverse means the products also can collide and break bonds and form back the reactants. Okay, which is typically what you don't really want, right? You don't really want to form back what you started with. Okay, you're wanting to form something new. Okay, so if we look here, okay, would you call this a product or a reactant favored reaction? Do you think? Reactant, yeah. So this is an example of where your reactants, you have higher concentration of reactants than products. So if you were drawing these arrows, so a lot of times you'll see this, you would see that you may have a small little one here and then a bigger one here, showing that it mainly drives to the left. Okay? But yet we got some product, but not as much as you would want. Okay, but if we flip this reaction, so here we started with SO2 and then we streamed in oxygen gas there, okay, to form SO3. Wasn't very efficient. Okay, but what if we reverse this and we take SO3 and we decompose it, okay, and to form SO2 and oxygen. So if we flip this around and we reverse it like this, now do you have a product or reactant favored reaction? Product, exactly. So we just flipped it, okay, and so the reverse, the product is favored. So we consumed our starting material and we formed our product. Okay, but notice, this is equilibrium. This is where the rate of forward and reverse is equal, okay, but does not mean our concentrations are equal to each other, right? Okay, because look, at equilibrium, these are the concentrations that we have, okay, and they're not equal to each other. So you can have a forward or reverse favored reaction. Okay. The concentrations that were shown, what I just said, these are equilibrium concentrations. That's what we call these. So if you look back at 0.076, 0.212, 0.424, those are equilibrium concentrations. This is going to be very important to us here in a few minutes. Okay, so if we think back to Chapter 16, we had a constant. We had a rate constant, K, right? And you all knew how to derive your equation from experimental data, and then you were able to solve for K. Okay, everybody remember that, hopefully? Okay. Well, now we have a forward, rate forward, okay, so equal to K forward times the concentration of reactants, okay? But we also have a rate reverse too, right? And they're both equal at equilibrium. So we would have a rate reverse, but now if we look at it in reverse, here C and D would be our reactants, right? Everybody see that if you look at it in the backwards way? Okay. So both of these rates for forward and reverse are going on here because we have a equilibrium reaction noted by the double arrow there. Okay? So if the rate of the forward equals the rate of the reverse, so I just took that K times concentration of A and B, K for C and D, okay, we can come up with a new constant. Okay? So I just set those equal to each other because that's what we said. Equilibrium's when the rate equals each other of the forward and the reverse. So I took the forward and the reverse, and they equal each other. And then if I rearrange and get both of my K's here, I end up with K, F over KR, equals the concentration of C and D over A and B. So it looks to me here that I have product concentrations, if you're looking at it from left to right, over the reactant concentrations. Okay, well, CF over CR, or excuse me, I'm talking right, KF over KR, okay, these can combine, and we just call this the equilibrium constant. So this is what it looks like. We take KF over KR, and that equals KC. So this is our new constant. So we had a rate constant in Chapter 16. Our constant in Chapter 17 is KC. Okay, it's also written as, you'll see it as KC and KEQ, because K equilibrium. So that's what that EQ is. Okay, so if we combine KF over KR, and we get KC. That's our equilibrium constant. And we saw how we rearranged, and we got product concentrations over reactant concentrations. Okay, so if we look at a general reaction again, we can define a constant, our Kc, okay, as product concentrations over reactant concentrations, each raised to the power of their coefficient. Okay, back in Chapter 16 in rate, I said, absolutely do not look at your reaction equation, right, to help you with anything. Okay, well, this is different. This is opposite of that. You do look at your reaction equation, and you get, so how many ever moles, so say if everything was 1 to 1, then those would just be, 1 and 1, 1 and 1 there. Okay, another thing, this must be in the gas phase. So for you to find Kc, your reactants and products have to be in the gas phase. So you may have to heat your reaction or change conditions to get everything in the gas phase. So that can be kind of tricky. But good thing for us, most reactions have been done, the ones that are known anyways. They've already been done for us, so they're already given Kc values. Yes. The what? No, there's no order here as far as what you're thinking, because our rate is constant. So we really don't have an issue of, if we double the rate or we change the concentration. Now all we're going to look at is the coefficient in your reaction equation. Yeah, that's going to be what changes and makes Kc different. So everything I just said is right here. So this is kind of wordy, but you can read through it there. But it basically states that Kc or Keq is an equilibrium constant, and its products, concentrations. Remember, concentrations in what unit do we put for concentration? Molarity, exactly. Okay, each raised, excuse me, I'm losing my voice, to the power of the coefficient in the reaction or in the balanced equation. So I'm pretty sure most times I give you a balanced equation, but most all of you, hopefully everybody knows how to balance a reaction equation anyway. So, but you're going to put those numbers there. Those are exponents, so it's a superscript there. And then once you calculate this, if you get a number greater than 1, that means the reaction is product favored. Okay? If you get a number less than 1, that means it's going to drive the other way, and it's going to drive left towards the reactants. Okay? Notice in red here, you have to plug in concentrations at equilibrium into this equation. Okay, so that's going to become an issue for us. We may have to solve for this. Okay, right now we're going to look at the simple equations first. Okay, but this right here, when you look back at those graphs we just went over, we have to know the concentration at equilibrium, meaning when the rate of the forward equals the reverse. Okay? So when you mix chemicals, it may take, a minute or so. It could take an hour for the reaction to reach equilibrium. Okay? So when you, drop reagents in there right away, that doesn't mean you're at equilibrium in 1 second. Okay? So it takes time to reach that point. Okay? So what we want to know are the equilibrium concentrations. So when the forward and the reverse equal, what are those concentrations? Okay. So Kc is constant at a given temperature. Okay. It will change if you change the temperature. Okay. So we call this disturbing our equilibrium. So we'll look at calculations later, not today, when we disturb equilibrium, and then we're going to change our Kc. But other than that, your Kc doesn't change. The only thing that it can change is if you change temperature. So that would be you start the reaction at 0 degrees C, and then you're at equilibrium, but then you change the temperature to 100 degrees C. Okay, that would be an example of where Kc would change. Okay? But it does not depend on initial concentration. So that's what I said just a minute ago. It's when, if you have known concentrations of two reactants and you put them in, a reaction vessel together, that's their initial concentration. We want to know for Kc what the equilibrium concentration is. So when the forward and the reverse rate are equal. Okay, so start with something simple here. All of these are gases. So unless you're told otherwise, these are gases, which we know we have to do Kc, we have to be in the gas phase. Okay, so we're at 500 degrees C, so nothing changed. Our temperature hasn't changed. We're not going to do anything like that yet. If we look here, we have an equilibrium reaction, so we see that with our double arrow. We have a 1-to-1-to-1 ratio, so if we write out Kc, we're going to have products, concentrations over a reactant. So that is our form of Kc. Okay, if you were given the values, then you would just plug them in and get your answer for Kc. All right, what about this one? If you were to just write out the form, write out your Kc expression. So Kc equals what? So looking at this equation here. Everybody write that down. Product concentrations over reactants, right? Okay, so our product, we have 1, and we have to square it, right? Everybody agree with that? Okay, it's only the coefficient, so don't look at, H2. You don't put a 2 out up here. Okay, that's a 2 that belongs to that compound. It's only looking at just the coefficients, so the numbers out front here. Easy enough? Okay, let's do this one here. All worksheets, and I forgot. Yes, I did. if you have to plug in numbers here, so say you were plugging in concentrations, really everybody usually gets the expression done just fine. Just be sure you remember and know how to use your calculator to put in something to the 4th power times whatever this number would be to the 5th power. So usually it's just a calculator issue if you don't get these right. Our KC has no units. It's dimensionless because all of our units cancel. So that's kind of the idea. So everything is equal. So when we don't have dimensions, we call this an activity. That's just a term that's used in chemistry. And all of these activities here are in molarity, right? Because that's what we're doing. We're taking concentration in molarity times another concentration. And so they all cancel, and we're left with no units. So that's one time, not one time. There's a few times in chemistry you don't have to put a unit, so this is one. Okay, so this is a pretty simple problem. We're just plugging in, we're writing out our Kc. So we already did this one. It was one of our first ones. So we have Kc is equal to product concentrations over reactant. And they're all raised to the 1st power because you just understood there, okay, because we have a 1-to-1-to-1 ratio. The key here is when you read the problem, it says that we have equilibrium mixture, okay? That's telling you that these are equilibrium concentrations because we know we can't plug anything in here unless it is at equilibrium, okay? So this is a pretty simple one because we don't have to find that concentration, okay? It's given to us. Okay, one thing to note here, we have 0.172 moles and 0.086 moles and 0.028 moles, okay? Do we plug moles into here? What are we plugging in? Molarity, right? Okay, moles and molarity are not the same thing, okay, unless you're in a 1-liter vessel. Okay, so if you're in a 1 liter, then yeah, they're going to end up the same. So if you take 0.172 moles, divide it by 1 liter, you get 0.172 molarity. However, if this was a 2-liter equilibrium mixture, then you would have to take those moles and divide by 2. So you have to really pay attention to whether I give you moles or molarity. Okay, if I give you molarity, then you just plug it in. Okay, but if I give you moles, you have to divide by the liters. Okay, but here it's 1, so it doesn't make a difference. Okay, but you take your product, so 0.172 molarity, 0.086, divide it by the reactants, and we get a Kc of 0.53. All right, so what's the point of that? What's Kc tell us about this reaction? What was the point in doing that? Okay, Kc is less than 1. So this reaction is going to be reactant favored. Yeah. So it's going to drive more to the left here. Okay. So this is what we did here. The Kc is 0.53. Kc is less than 1, so it's reactant favored. Okay. However, if we flip this reaction and look at it in reverse, what do you think is going to happen? It's going to be product favored, right? Yeah. So usually in one direction it's going to be, reactant favored, and in one it's going to be product favored. Okay. So if we do that, let's flip it. Okay. So now our products that were the products are now our reactants. Okay, so this is, we would start the reaction different. We take PCl3 and we take stream in our chlorine gas and we'd form PCl5. All right, so if we take these concentrations, okay, they were the same, we're keeping them the same as the previous problem, we get a Kc of 1.9. Okay, so that's greater than 1. And so this would be product favored, okay, when we reverse it. Also, if you look at a forward and reverse reaction, like we just did, we just flipped it, they have a relationship between each other, and that is that they're going to be a reciprocal of each other. Okay, so we didn't even have to go through this. We found our first Kc was 0.53. If we take 1 divided by 0.53, we get 1.9. Okay, so that's the relationship of a forward and reverse reaction at equilibrium. Okay, you can go ahead, of course, and go through this, but they have a reciprocal relationship. So if you find 1, so let's say it was, well, here it was 0.53, you can take 1 divided by 0.53, and that gives you the Kc of the other direction. Okay, so that's just their relationship. Does that make sense? Kind of? Okay. All right, so far we've been given equilibrium concentration. So we just plug those in. We raise it to a power if we needed to, if it was a, more than a 1-to-1-to-1 ratio. Okay, now we're going to look at a situation where we're not given the concentrations at equilibrium. Okay, so we have to solve for equilibrium concentrations. Okay, and this is not too terribly difficult. It really all comes down to looking at your balanced equation. So that's really what it comes down to. So we use the ICE method. I stands for initial. So you're going to be given some kind of initial concentration. You have to be given that to be able to do the problem. Okay, and then you're going to look at a change. So you're going to have a change in your reaction. And then you're going to finally, at the end, you're just going to do a simple addition and subtraction, and you'll get your equilibrium concentrations. Okay, and that's what we're going to plug into Kc. All right, so first off, just read the problem because you want to really notice the whole keywords introduced. Sounds like initial there. Okay, and then it tells you we have a new temperature. And then it tells you 1 equilibrium moles. And then we're trying to calculate Kc, the equilibrium constant. Trying to move this out of the way. Okay, so the difference being here, the last problems we looked at, we were just told the equilibrium concentrations or the moles are blank. Okay, here it's not so simple. We have a mole of PCl5 that was introduced into the container. Okay, so we have 1 mole PCl5 in a 1 liter container. Okay, so if we have 1 mole and 1 liter of PCl5, what's the molarity of our PCl5? It's 1, right? Because you just take your 1 divided by your 1 mole divided by 1 liter. That gives you 1 as your molarity. Okay? So if we think about what was just told to us was our initial concentration, right? It says it's introduced into the system. A lot of times I'll even say the initial concentration or the initial moles or whatever. Okay, so we're going to put that there under PCl5, okay, because that's the compound that we were told this for. Okay. At the instant that you put PCl5 into a vessel or into a container, you're not going to have any products for at least a split second. Okay, so these are always going to be 0, right? Because you initially don't have products until the reactant has time to react or decompose in this situation to form the products. Okay. Okay. The next thing we're given is at equilibrium 0.6 moles of PCl3 was present in the container. So we're given one concentration at equilibrium. Okay, so 0.60 moles divided by 1 gives us, here's our change. So for those 0.60 molarity. So at equilibrium, at E, we get 0.60. Okay, so our change here had to be what to get to 0.60? 0 plus 0.60, exactly. Okay, everybody with me so far? Okay. Now, all you do is we have one piece of our information for equilibrium. Okay, we also have an initial. Now you look at your balanced equation, and it's a 1-to-1 to 1 ratio. Okay, so we know that mass can neither be created nor destroyed. So we have to have equal amounts on each side. So if we lose a certain amount, we have to gain it on the other side. So if we gain 0.60, well, these have a 1-to-1 ratio, right? So we also have to gain 0.60. Okay, so this is a plus here, okay, because we're forming products here. Okay, we also have a 1-to-1 ratio between our PCl3 and PCl5. Okay, but are we going to add 0.6 here, or are we going to subtract 0.60? Right, because we are consuming our reactant to form products. Okay, so we've got to minus 0.60 here. So we get 0.4 and 0.6. Okay, now these concentrations are at equilibrium. So now we just plug those into Kc. So we take our product concentrations, our 0.60 here, and plug them in. And then we divide by our 0.40. It is still less than 1, slightly, so it would slightly be reactant favored, okay, because it's still not quite to 1. Okay, so the key here is to take the pieces of information that you're given, put them into the ICE method, and then base everything else off of your mole-to-mole ratio to give you the equilibrium concentrations. I wish I had this one not shown. Hang on. Let's see if I can. You're probably seeing the answer anyways, but. All right, I want you to try to do this one, and then we'll do it together. I know it was already up there, but. You have to know your equation. Okay. Go ahead and balance it. That's good practice. Balance the equation first, and then calculate Kc. You've got two reactants, and you're given their initial concentrations. Okay, whereas we had just one before, one reactant. When you balance, you should get this. Okay, key things is we're in 1 liter. Okay, if this was a different number, you'd have to divide by, so say it was 2 liters, you would have to divide all of your moles by that 2 liters. Okay, so there's some a worksheet. I printed it off and left it upstairs, but on it, you'll have to do that quite a few times. So this is just 1 liter, so we don't have to do that. Okay, but where are we going to put in the 0.80 and the 0.90? What are those? Exactly, so we'd put 0.80 molarity, because we divided it by 1 liter, and 0.90. Okay, initially we don't have any product. Okay, we have 0.20 moles of ammonia at equilibrium. So the key thing here is this right there. Okay, so we have 0.20 molarity, because we'd still just divide that by 1. Okay, so that means our change had to be 0.20, right? Okay. If we look at our relationship between ammonia, our NH3, and nitrogen, we have a 1 to 2. So really, we have half as much, right? So what we have to do is we have to half that number, okay? Because this is 2 moles, this is only 1, so we're going to put half of that into here. Everybody see how I did that, or why I did that? Okay, it's still our mole-to-mole ratio. So we have a 2 to 1, we have twice as much, so that means we could only have lost 0.10, okay, because there's only 1 mole of it. Okay, the hydrogen's a little harder to see because its ratio, mole-to-mole ratio with ammonia is 2 to 3. Okay, so what I do is I take, some of you probably see this right off, but just to kind of show you, I take this right here that I'm given, the 0.2, and then I just put up a ratio. So I have 2 moles from my equation. So I have a 2 NH3, and then I have 3 H2. So there's my mole to mole ratio. Even though it's not really molarity, but we'll just put that there anyways. Okay, so if we take 0.2 times 3 and divide it by 2, we get 0.30. So the 3 that I got up there came from here, and the 2, there's our ratio. So if we have 0.2 of this, we can't just double it. If that was a 4, then we could double it, right? Okay, because we have double the moles. But it's a 2 to 3, so you end up, adding 0.10 to it, because you're going to go up to 0.3. Okay, so we get 0.70, 0.60. So these are the concentrations that we will use. Okay, so the key things, you have to be given initials for your reactants, and you have to be given 1 equilibrium concentration to be able to solve for this. All right, so now we plug it into Kc, so I'm just going to go back to the previous slide here. Okay. So we take our 0.20, whoops, hang on. Okay. This is often forgotten. We have to square it, right? Because our Kc says we raise it to the power, or concentration to the power of the coefficient. So we have 0.20 raised to the second power over 0.70 to the first, because we only have 1 mole of it. And then we have 0.60 to the third power, because we have a 3 as a coefficient. That's often forgotten on accident. You find them and then just plug them in as they are, but be sure you remember these here. So it's 0.26 is less than 1, so this reaction would be reactant favored. Any questions on this? Oops. Okay, and this is just another way to look at Kc. If you were given, this is just algebra, so here we're given equilibrium mixtures, so we're not going to have to use the ice method, but we're given Kc, and we're looking for the concentration of chlorine. Okay, so if we write this out, the key word here is equilibrium for everything, so we know we don't have to use the ice method here. Okay, but what we're doing here is taking Kc is equal to products over reactants. All right, we're still in a 1 liter container. Okay. And we're given PCl5, PCl3, and Kc. So we're trying to solve for chlorine, the concentration. Okay, so all you need to do is rearrange that equation. So go ahead and do that. Okay, you rearrange it to solve for Cl2. So this is what we're looking for. Should get this right here. So then we plug in 1.9. We plug in 0.25 molarity because we divided by 1. And then we plug in 0.16. Okay, so when you do the math on that, what do you get for molarity? And they're all raised to the first power, so 0.25 divided by 0.16 times 1.9. 0.82, exactly. So this is just a way we can, if we know the Kc value, which for a lot of reactions we know what the Kc is, so there's tables that tell us this. So, and then if we knew a couple of concentrations but we didn't know one, then it's just algebra to solve for the one that we don't know. And now, because we're finding concentration, we would put molarity there. Okay, we're not finding Kc. Kc would have no units, but here we're finding the concentration. Okay, not just the concentration, we found the equilibrium concentration. Okay, because Kc is based on equilibrium. Oops. Okay. All right. I'm going to go grab I printed these, but while I go grab these really fast from my office, you can start working on these. So the first one is just write the expression for Kc. So we did one very similar. Okay, it tells you everything's in the gas phase. Okay, so when it tells you just to write the expression, all it is just to write out Kc and then the general expression there. Okay, be careful with number 3. Yep, coefficients become the exponents. Be careful here because you've got a solid and a solid. So what do we know about Kc? Has to be in the gas phase. So you do not include ones that are not. So they will not be in your expression. Okay, so that's kind of a one that can be missed sometimes. Yep. Exactly.